Welcome. All right, very good. Thanks everyone for coming along this morning. It's funny because when I was submitting my talk and thinking about names, I was like, well, there is so many things I want to talk about and we want to go through, we could possibly talk. And I really couldn't come up with any cool name, and everything I could come up with was so super boring, right? And it's like, with all these names, no one is going to go there. I'm going to be there by myself. So I better come up with something interesting. And hey, this is impressive, huh? So now I feel the pressure that we got to deliver something really interesting. So let's see how that goes. Yeah, we decided to call this one the art of powering the internet's next messaging system. And as you see that logo, by the way, how many of you guys recognize that logo over there? No? Okay, that's good. Okay, some of them. Okay, so a little bit of introduction about ourselves. My name is Juan, and I work at the Layer alongside with Mubarak, who will be co-presenting with me this talk. And we're both software engineers at the server team. And a little bit of myself, I've been working on Erlang since 2009. I wrote my master thesis about qubit quick check on testing. And my colleague Mubarak has been formerly at Apple. He's got a lot of experience with large distributed systems. And in addition to that, he's committed to the Apache Flume. So we'll be delivering different sections today, and I will kick it off. So this is going to be the agenda for today. We're going to start off by introducing Layer, the concept, and what Layer does. And then we're going to go through three main components in this talk. The first one is going to be Speedy. The second one is going to be message routing. And the third one that we're going to go through is data infrastructure. After this, we will go through several topics about performance and problems we faced and difficulties we solved and lessons learned, of course. Then we'll open it up for 10 minutes or whatever is left for questions and answers. By the way, feel free to stop me anytime if you have any questions or any comments. They're more than welcome. So what is Layer? Layer is building the open communications platform for the internet. What that means is that we make it very, very simple for app developers to add communications features to their mobile applications, whether it's photo messaging, text messaging, video messaging, location sharing, generic data synchronization. We make it very simple, and we take care of all the difficult things of communications, whether it's backend storage, typing indicators, push notifications, anything. And how is this even possible? OK, so we develop client SDKs that make it possible for those mobile applications to integrate our system and talk to our servers. So with very little effort, you can integrate messaging features and communication features into your app. But of course, like, why should you trust someone like Layer to do communications? What is so hard about communications? Everyone can do communications. Well, pretty much everything. Client-side storage, network transport, cloud storage, data synchronization, offline states, global infrastructure, security, push notifications, multiple device scalability, policies, regulations, a lot of difficult things that you don't have to take care of if you only want to focus on the experience to your customers. And obviously, make it available across all the platforms. So the way we see things here is that when you're an app developer and you're developing something for your mobile application, in the same way that you want to add geographical features to your app, you're not going to build a mapping system from scratch. You can go out there and integrate things like Google Maps, Apple Maps, Yahoo Maps, and get it already integrated right away. Same happens with payment stacks. You don't want to build a payment system from scratch. You can hook it up with an available API and get payment features that can work out of the box. So that's where we want to fit in the communications. And we want to make it simple for everyone to add communication features to their apps without having to take care about the difficult things. In other words, you focus on the customer experience, and we take care of the most difficult thing. OK, so a little bit about our software stack. This is very, very simplified. And as I mentioned before, we develop client SDKs that talk to our servers. Obviously, they are written in their own native platforms. And today, we've got Android and iOS SDKs available. We're on the works to release Windows Phone and JavaScript for the web. And then our all backend systems are mainly powered by Erlang systems with Cassandra as a data storage solution. We also have other additional components written in Scala that help us with services like policies, reconciliation, and so on, but they are totally out of the scope for today. And the OS of choice for us is CoreOS, where everything runs on top. So the question, why have we chosen Erlang? Well, like as we saw, all of us in the keynote, the main use case that has been invented for is communications, right? And that's what we're about to solve. We're in this world, and this is a natural fit for Erlang, right? We also want to achieve fault tolerance in our system, because we want to make our service available to all our users without having to experience any downtime. And by using the best practice of OTP, that help us a lot not to be across with any problem with issues in production. Especially concurrency model, message passing, not being able to share any data across processes. Very helpful. It also gives us the ability to handle a large number of concurrency processes. And especially, this is very important too, is the ability to handle binary protocols, especially when you are talking to APNS, DCM, and Kafka, for example, that we do it on a daily basis. So how does the layers backend look like in a nutshell? Well, super simple. As I said, we've got our client SDKs that talk a speedy HTTP to our system. We have a Cowboy running as a web server, speaking 3.1 protocol of SPDY, and that happens to be handled by our core engine that is smart enough to route every request to the right queue, and at the end of the request, that gets delivered somehow to the right recipient. Obviously, there is a lot of complexity and logic in between, such as storage of a lot of metadata and information about everything related to the communications that happens to be stored in Cassandra. OK, so as I said, these are going to be the three main components we're going to go through. I'm going to go through the first two ones myself, and then Mubarak is going to deliver the infrastructure. Just to start off with this question, how many of you guys are using Cowboy in production? OK, maybe half of the audience. And how many of you guys have been working with SPDY in Cowboy or in any other web servers? Just a few. OK. All right, so we happen to be using both, OK? And for those of you who don't know what SPDY is a sort of evolution of HTTP 1.1 and happens to be the predecessor for HTTP 2. It's not meant to be a replacement, but it's meant to be an upgrade in the way that it looks at improving some of the issues that HTTP 1.1 has, and such as latency reduction, which is the main goal. Also, one of the other goals is to improve the security. So we at Layer rely on SPDY protocol for transferring our content from clients to servers and so on. And the two main features that help us achieve the latency reduction is the compression of headers defining the protocol. Basically, a speedy connection keeps track of all the headers that has been sent. And for those of one that have been already sent, they are not sent anymore. So that's avoided. And also for the new headers that are being sent, they are compressed. And then the multiplexing that happens to deliver sub-resources of a content to the client that is requesting it within the same connection. So it's also more efficient. A little bit of history about the protocol. Well, there has been a few drafts written. Everything started off in 2009, and then the second version came out, the third version, 3.1, and the latest, the version 4 has been on summer 2013. SPDY, as I said, is an open networking protocol, and not all the versions are implemented everywhere. The most commonly implemented are the 3 and the 3.1. And today's browsers, most common browsers, Safari, Chrome, Firefox, they are implementing those. And as we can see here, the Cowboy project added basic and experimental support in spring 2013. And we happened to take it from there. So the whole implementation of the protocol obviously is not fully implemented, but what is available is split up across these two modules. If you're familiar with Cowboy from some releases back, I don't remember which one, there wasn't a split up in terms of the common libraries that were supporting Cowboy and Cowboy itself. So in the Cowboy SPDY module, we've got the protocol implementation. And basically what it is the main loop that handles frames and coordinates all the replies to the clients. And then we've got the Cow SPDY, which helps you work out the protocol manipulation and also the parsing and building of the frames, settings, and streams, and so on. So yeah, we all know that Cowboy is a pretty well-maintained, probably one of the most popular Erlang projects in GitHub. And well, it's great to feel that it's got a lot of support and attention. So one of the things that we discovered of the protocol that were beneficial for us, unfortunately, they weren't implemented in the Cowboy app stream project. So some of those features were things like server push, rate limiting, and flow control. Server push is very beneficial because it gives you the ability to stream and push content from your server without requiring from the client a specific request. So it becomes more efficient once the SPDY connection is established. It's a similar concept that what you get with WebSockets. Then you've got rate limiting and flow control, which happen to be two flavors of limiting resources. The rate limiting option is to limit the number of concurrent streams per second, and then the flow control, which limits the amount of bytes that the client is allowed to send. So what happened with that? Unfortunately, those were interesting features for us, for the performance we wanted to get. And we obviously, when you want to contribute, you're meant to fork the project, implement yourself, submit the pull request, and so on. But the pace we were working at made it pretty difficult to be on top of things and merge it back upstream. So things got a little bit delayed. We are implementing all these 3 advanced features on our branch of Cowboy. And as of today, rate limiting feature is a pull request that has been submitted, hopefully merged soon, and we want to get the other ones merged as well. So that was the first. That was the first part. Any questions so far? Yeah.
So
Yeah, okay, so the question is if I can talk a little bit more about the SPDY compared to HTTP 2, and if Cowboy is going to support HTTP 2. The answer for the second question is I think is yes, but I think as Loic told me, that's going to be released alongside the new version, the new major release of Erlang distribution. So he's waiting for that, and so the spec for the HTTP 2 was released by Google last month, so it's been already finalized. And as far as I've read, everything of the spec has been inspired in what SPDY defined. So SPDY basically was a foundation for what HTTP is today. I can't really know the fine details. I don't have them on top of my head, but that's all I can tell. Yeah?
Also, the choice of using SPDY and using a single connection, how does it work with other applications which are still using a multiple connections? Have you seen any issues with that?
Well, I mean, the thing is that we have control over everything, over both ends of the connection, because we are implementing the client SDKs. So we decide what protocol we're talking to our own servers. Then, since we have control, we decided to go for something more efficient than regular HTTP 1.1. And today we're talking SPDY from those devices to our servers.
I was thinking maybe browsers, because we have other...
Yeah, we are not supporting web yet. So of course, when that happens, either we will be on HTTP 2 or WebSockets or something that can be fully compatible. Yes?
Did you make a pull request to the Loic repository?
Which one?
The Loic repository.
Yeah. So the rate limiting is submitted. It's been submitted there for a while. I think everything is good to be ready, but he's super busy, so hopefully that will happen very soon. The other two ones are not very easy because we have to do some, well, it's a lot of work because we've changed quite some things, and we've got to isolate those changes and then put them on top of current master and send it upstream. So yeah, it's on the works. Hopefully that will happen soon. And I will go over this later on the lessons learned section, but this has been one of the most painful experiences, because once you fork it out, especially a very, very popular project, then you struggle to come back again to depend on the upstream, and that's not something I recommend to anyone. Yeah?
Why did you decide to go with SPDY if you would have to rewrite it with WebSockets or for browsers anyway?
Well, I mean, those are decisions attached to a roadmap and product decisions. Like at the time, maybe we weren't still planning to do web or whatever, and we were only focusing on mobile devices. And at the time, choosing SPDY over what was available was more convenient for us. Also, as far as I know, maybe Mubarak has a better answer. Support that you get from iOS and Android at the time was very good for SPDY. And implementation were already pretty mature, so that was a good decision for us. More questions? Okay. Yeah, so feel free. You're welcome to check the project out. Unfortunately, the documentation is not updated. Everything is still as the original README. But yeah, things are working in production for us. We're using those features continuously. Okay, so message routing. Obviously, when you're building communication systems, routing the right message to the right recipient and so on becomes very, very crucial. So we've designed a very, very trivial and a simple solution that is able to scale out and also deliver right messages to the right recipients, whether they are connected or disconnected at all the times. So the main concept here is that the layer messaging platform publishes every single message to a RabbitMQ broker. And things that I describe are as simple as this. When the post method arrives, well, obviously we handle it, and then after doing all the parsing and checks and things like this, we send that message across to the broker, and that's received there until is properly stored in the right queue. So this is how things look like. We've got a sender device here establishing a speedy connection to our server. That server happens to have a connection and obviously channels to RabbitMQ. And then when a device connects to layer, like let's say a recipient for that conversation, a queue for that device gets created. Okay? So this is how things look like. Super, super simple again. All talking AMQP client by the RabbitMQ guys. So we declare the queue. All we need our channel, the queue name, arguments for the record, and then at the same time, attached to that queue, there is going to be a process that is going to start consuming that queue and listen for incoming messages. I'll explain in a second what that means. So this is how things look like. On the receiving end, we've got a Android device establishing a speedy connection, and then that's going to create a specific queue for that device. There is a second guy getting connected. We've got a second queue, and so on. So that can scale up to, well, we've got thousands of queues running our RabbitMQ cluster. And when a device comes in online and establishes a speedy connection, we've got queues. And then if they go away, if the connection closes, then the queues expire because we've set those rules when we've got no messages inside. So there is a process per connected device that consumes messages from that device queue, and that's what it happens. That's what it happens when we start consuming the queue. So we've defined a behavior called already. Oh, okay. Well, I gotta go faster. Sorry. Yeah, we've got this process listening for the messages that are going to be handled by a OTP behavior that we defined that handles queuing, handles the queuing, handles channel connection, and so on. And this is how things look like. We've got the AMQP message, and then we get that to whatever handler we've got, and that's going to end up in a server push from the server to the receiving device, right? And this is how things look like. Well, this is irrelevant stuff, but basically when we do the speedy push, this is basically going to call what we implemented, the server push feature in Cowboy. This is going to send the 200, the path, and then eventually the push body we're streaming to the device. So let's go very quickly through a example. Let's assume we have a 4-device conversation. Okay? So the first guy sends the first post. That gets handled by Cowboy. We send a AMQP message to the broker. That gets routed through the routing keys to the right queues, and that gets delivered to the guys participants on the conversation. But what if those guys waiting for or participants of the conversation are not connected? Obviously, we are not going to have queues, right? So what's going to happen here? Okay, well, we need those guys need to get notifications regardless of their connectivity status, right? We've defined also a what we call platform queues, platform pushes queues, where they have been defined with match all binding. What that means is that all the messages will also be going through that stream, and that freeway is going to end up in either the APNS server or the GCM based on a lookup in our storage that tells you whether that device has been registered as an iOS or an Android. Okay, that's pretty cool, but how do you manage connectivity resources? I don't know if you guys have been yesterday on the Anthony's talk about pooling libraries on Erlang. I found that very, very interesting because we are dealing with those things every day, and some of the libraries that he mentioned, we use them in production. And the solution is very simple: pools, 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 and more pools. Okay, so for the speedy connections, it's a no-brainer. In 99s have created this Ranch library that is a socket connector acceptor pool. that defines a gen server that manages connections, listeners, and ports. And what that gives you is the ability to control all the established connections that you've got in your web server. And besides other cool things, you've got this callback that what that gives you is the number of, in this case, speedy connections you're running. And when you attach that to a monitor system, you get things like this, where you can visualize all your samples of current connections at all the time in your production servers. But how about AMQP connectivity, right? In the AMQP world, we've got connections and channels. Connections are TCP connections, and channels are lightweight processes that happen to be within those TCP connections. So they are all multiplexed to one real TCP connection, right? So, sorry for being very, very fast, but I just...
If you have more extra time, they're extending it 20 minutes.
Okay, good news. Well, stop me if you have any questions. But so basically, what the problem we have to solve here is that we wanted to have a system where we were able to scale out and scale down AMQP resources as needed, right? So your system is dynamically sized. And what we did was to develop a two-layer pooling system based on connections, and per every connection we'll create as many channels as needed. And we did it with Pooler. I don't know if any one of you are using Pooler in production here. You guys? OK. Because, well, I'll tell you in a second, but we've got some issues that we managed to understand, but they were pretty tricky. Although it's a pretty well-maintained library and obviously OTP compliant, so yeah, I think it was probably one of the best in the list that Anthony mentioned. But things are super easy. This add node callback is what we get when our service discovery system discovers a new RabbitMQ node in our network, and that's going to end up creating a new pool of connections that well are predefined in the number by whatever variable we've got, and then we're going to call a start connection method that happens to be in the same module. What that gives us, I mean, you notice here that we're not obviously, we want to open a connection of pools, but we're not giving the callback for AMQP yet. What we're doing is doing a wrapper, and what the wrapper does is that it obviously calls AMQP connection to open the TCP connection, but it also, right after, calls, tells the same gen server that the connection has already started. And that makes a subpool inside that connection. So we take that connection P that has been returned by AMQP, and what we really call at the end is AMQP connection open channel. So that's going to start off with 10 channels per connection, and that's going to be dynamically sized as much as we need. This is what I was talking about, the cooling feature. So this is basically a feature that Pooler has that helps you to cool stale connections or stale resources, whatever they are. And when you use RabbitMQ, or in this case AMQP client together with Pooler, there is a lot of odd behaviors, and because what the cooling does is that it sends a exit with a kill reason to the channel, and AMQP understands that or turns that into internal error with a specific code. So what happens is that you end up killing the connection, because that's what AMQP does when it gets an internal server error. And what's going to happen is that that connection that a lot of channels depend on are gonna be killed as well. So it's a total mess. And when you're talking about thousands of channels that you are multiplexing in your system, the mess becomes huge. So of course we had to disable that feature. That didn't help at all. Okay, so I'm going to hand it over to Mubarak, who's going to deliver the section of data infrastructure right now. Yeah.
How do you deal with errors like are your messages persistent in AMQ? I mean, what if the whole server dies and all your messages, because by default they are volatile, right? I mean, they are just in memory.
Yeah, well, did you mean the persistency mode we write RabbitMQ messages, or? Yeah, non-persistent.
So they're not persistent.
No.
The whole thing can go down and you lost all your messages.
No problem. Yeah, but the problem is that when you're talking these situations, the mess that you get when you do the channel closing is huge. So I'll go over that afterwards.
Thanks, Juan. Hi, Mubarak. I'm Mubarak. I'm going to talk about data infrastructure. Layer communication platform leverage big data and distributed systems to build internet scale large volume messaging infrastructure. So we use like a lot of Apache projects like Cassandra, Kafka, and we use ECAF, which is Erlang Kafka client to produce data, Zookeeper for service discovery, config management, and Apache Spark for the in-memory data analytics. And we have a homegrown Scala consumers as well as Spark streaming jobs. Apache Cassandra is one of the critical component of our data infrastructure, meaning we store all messaging events as well as all the messages inside the Cassandra. Whenever the new app developer comes on board, we create apps management, credentials, policies, certificates, all other application related stuff and store them in Cassandra as a more of a authentication scheme. And whenever the messaging comes online, whenever like users send messages, we store messages and events as a source of truth in Cassandra. We are using Cassandra for two different things, one for online real-time services and second thing for offline analytics data store. This is how our data infrastructure look like. If you see the left-hand side, all the services are built using Erlang, and the middle and right side are data infrastructure, and we are leveraging a lot of Apache projects, as I said. So services internally uses ECAF, Erlang client. Whenever the service encounters an event, it publishes the metric to Apache Kafka. Then the Apache Kafka internally has a lot of brokers, topics, and partitions. Then the homegrown consumers can read the data, do real-time computation, and push the aggregated results to Cassandra cluster such that the in-house dashboard as well as the developer customer-facing dashboards can view the data in near real time. So we use two different consumers. One is written in Scala, and another one is Spark streaming job. We play around with Spark streaming job now, but we have been using Scala-based consumers since it went into production. Now I'm going to talk about how we use ECAF, which is an Erlang client for Kafka. So we did research on several Erlang-based Kafka clients, and we are happy with the ECAF because it's working pretty well. We load tested. It is high performance. It's very lightweight. It creates workers based on need. So whenever new Kafka broker comes online, it automatically creates the worker for you. It internally uses GenFSM and GenServer modules to do the worker management. You don't need to query the Zookeeper to get the metadata about all the Kafka brokers. If you supply the only one broker address, the ECAF client takes care of fetching the metadata information about all the Kafka brokers. And it does very smart way of connection pooling, all other stuff. We can use synchronous way of sending metrics or asynchronous way. Even if Kafka broker goes offline, ECAF takes care of buffering your data inside the service, and whenever the broker comes online, it transfers the events from client to broker. We are streaming messaging metrics such as how many messages have been sent for an app, about message delivered, how many message read for an user. Sound like for application management, how many active users are there for an app. like authentication related stuff, like how many auth errors happened, how many authentication successfully happened, related to push notification, how many pushes are sent from our infrastructure to devices, how many push notification errors, and how people are using our SDK versions, app related metrics and user related metrics. We have around 150 metrics we are storing. Sorry, I can't put everything here. As I said, Kafka is our backbone, data backbone, and we are using as a data freeway. It's a distributed, partitioned, replicated commit log service, and it provides pub/sub messaging model, which is from LinkedIn. So we can store all the messaging events and metrics inside a topic, and each topic can have multiple partitions. We are having a set of brokers which is called Kafka cluster. We are basically using replication factor of 3 to basically address all our high availability concerns and single point of failures. We are playing around with transferring all our application level logs, private logs, public logs, search infrastructure logs to Kafka, such that we can write our own consumers to fetch the data from broker and process it. Then, sorry.
Quick question about the Kafka infrastructure. Is that purely for analytics, or?
We are using like a Kafka only for purely data analytics. Oh, okay. Is that your question? Okay, thanks. And we are leveraging Apache Spark, which is from AMPLab for lightning fast data processing. We have a lot of in-memory aggregation jobs like monthly active user calculation, daily active user. If you want to find how many devices being involved in the client to server messaging pattern, if you want to run summary jobs like daily, hourly, weekly, kind of app based stuff, and we are creating a data pipeline to build data service on top of existing data. We are working on Spark streaming to get the near real-time events and aggregation of jobs so that we can give near real-time visibility to our developers. We are working on Spark SQL to give ad hoc queries for external customers as well as our business team. We have written so many like a data validation and migration tools to leverage Spark. Any questions related to data infrastructure? All right. Oh, sorry.
Yeah, I had a question about, it seems RabbitMQ and Kafka could have similar goals. Why did you choose Kafka over using the same tool?
So like we believe that RabbitMQ for pure messaging, and we believe that Apache Kafka for log-based analytics infrastructure, and those two are very like a vertical. I don't think like both of them is going to solve all the problems. Okay, thanks. I will give it to On.
Can you hear me? All right. All right, I'll try to be fast. I know we've been we're a little bit delayed, but I think this is pretty interesting, and I also want to hear your feedback in terms of you guys have been through the same things, because it's all about learning here, right? Well, before I start, I don't know how many of you guys are following the mailing questions list of Erlang questions list. Because of course it always happens the same thing. You sign up, you start following, and then after a while you just get a lot of unread messages that you never followed. But specifically this one in January of this year, Roberto Stinelli started up, explaining what the behavior what he was seeing in his production server and memory accumulation. He didn't really know where to look for, and that led into a huge thread that I consider is very, very interesting to learn about how the VM works, how the garbage collector works, and how to dig into memory analysis. So I definitely encourage you to check it out, because you are going to learn a lot if you know already. Hello? Okay. Yeah, so some of the challenges of building a communication system like this are always the same. You deal with memory accumulation, memory weird patterns that you don't understand, especially when you're monitoring them. We particularly found problems with our Cassandra driver. We use CQ ERL. Anyone using Cassandra here in production with Erlang? No? You guys? What? Huh? Yeah, what driver do you guys use? You guys just wrote your own one? Yeah. Is it open source? Okay. Well, we didn't have time for that, so we went to GitHub and we grabbed the best one we thought it was. And yeah, you know, obviously it talks well the Cassandra binary protocol, does prepare statements, a lot of cool features, but we've found some bottlenecks and issues that we amended. We've forked it out, so it's again in our repo. Not all of the fixes are merged upstream, but we're on the works. Some of the interesting things that we found out was the famous shutdown by the Erlang VM when you get to reach the max restore intensity. And I think, well, there are a few reasons there, but I don't know if any one of you are using Supervisor 2? How many of you know what Supervisor 2 is? Okay, well, Supervisor 2 is basically the main OTP supervisor that is being written by RabbitMQ that adds a few features on top of that and it makes it more secure, such as when you get to make a mistake like this one where you do template copying of the max R and max T parameters for your supervisor, you end up you know, making these mistakes where the whole thing goes down just because you didn't really think about the right strategy or the right numbers. Not obviously all the supervision trees deserve the same parameters. So that's a very common problem that you had to study well. Rebar and reproducible builds, that's been a pain for us. We have a great hope with Rebar 3. Fortunately, that's going to help a lot. And as I said earlier, trade-offs when forking out popular GitHub projects. If you don't want to be maintaining the project by yourself forever, you should be careful and be merging upstream very fast. So some of the lessons learned. As I said, the Supervisor 2 is very, very helpful for when you are not very confident with your supervisor strategy. Some of the issues we faced that were trickier was the abnormal heap growth that I think is called. Then in the next session, Lucas Larsen is going to talk about the Erlang VM and especially some of his studies about the GC. That's very, very cool, and I'm going to explain in a second what we saw in production. And one of the most important lessons we've learned definitely was the fact of monitoring everything you can, especially when you're running in production. Anything that you can imagine that can lead to an issue or a memory leak or a problem or a bottleneck, monitor, build your graphs, build your gauges, get your dashboards on, and then watch it out. And then based on that, you will get a lot of output that can be helpful for understand your problems. Problems we had with Cassandra eventual consistency and not being able to synchronize the cluster times. That's been a pain, but well, I mean, I'm going to skip that because it's more DevOps work. And as I said before, the RabbitMQ together with the puller behavior when you're using the cooling feature, that has been a pain. And last but not least, I think this is a very interesting one. Lagger, as you probably know, has this feature where you can define a high watermark threshold that where you get the speed rate of log messages higher than that, it just gets ignored. Which is, I think, is a very, very dangerous thing to enable in production, especially when you're debugging, because you're going to obviously miss out a lot of problems that happen, and they're going to get ignored. So my recommendation is be very careful with that. And something else that I found out is that Lagger implements this feature as in that by default is enabled. So be careful with that, because if you want to get it disabled, the only way to that is by explicitly say undefined. By default, I think it's defined to 50 or something. Okay, so I want to show you this specific problem that to me was extremely particular. This is the fact. We're running production. I'm monitoring my system, and all of a sudden things seems to be healthy, seem to be reasonable. All of a sudden, I see the memory distribution of the VM change a lot, especially for the Erlang processes. Okay, so I see a huge spike, Then next thing to do is to understand what process or what processes are gathering all that garbage or memory, right? So you list the number of most memory consumer processes in your VM, and then you found out that the error logger has a huge heap. And this is my face. I don't know what to do there. And well, I mean, the first thing that I can come up with is just cry, right? And it's like, oh my God, this is gonna, how are you gonna solve this? Why? I mean, I don't understand why Erlang is doing this to me. So let's force to run the garbage collector, okay? So if you do that, well, shrinks to nothing, so problem solved, right? But yeah, I don't want this to happen. What's the reason behind this? Like, any ideas? Yeah?
Accumulating binaries?
Huh?
Not garbage collecting binaries?
Binaries, no, it wasn't binaries. It was related with something that I explained before. AMQP together with Pooler, a lot of cascade issues, channels getting killed, a lot of error messages. If you're talking about thousands, you multiply, and what happens is that this is our hypothesis after talking with Lucas from Ericsson. Let's say that you have a large burst of messages on the process all of a sudden, 100,000. So, and where those messages probably come from? Well, in our case, it's because we have a cascade issue where one channel is being killed by Pooler, and that provokes a huge disaster, and all the channels get killed. Of course, that sends a lot of messages to error logger, right? So error logger is going to sit there, receive all the messages in the mailbox, and the mailbox is going to grow very fast, right? So if the process kicks a garbage collector at a time, as an optimization, apparently, those messages that happen to be in the queue are going to be copied to the heap, okay? So obviously the side effect of this is that the heap is going to have to grow as much to accommodate all those messages. In this case, as we saw here, we're talking about 6 GB all of a sudden. And yeah, so then the GC will be triggered, which is going to release the messages, but the heap is going to remain very, very large, right? Even though the messages are having flash and everything. Because the heap shrinking algorithm won't happen until the second GC kicks. And even when that happens, the shrinking algorithm is going to happen on a 25% basis. So it's not going to be gone completely. The error logger heap is going to be still huge. So what is the outcome? You end up with a normally large heap for error logger. Okay, and this is all other things that happen there, always with error logger. And so what solutions can you come up with? Well, my recommendation is monitor very carefully the processes that are sensitive to this issue. In this case, very possibly for error logger. And you can obviously trigger a manual or based on whatever monitor system, a garbage collector whenever you want, because the garbage collector is going to be more aggressive than whatever is kicked by default, because it's going to compress YAML and the regular heap. And if you want to read more about this, there is this paper that Lucas Larsson wrote, sort of a draft, and he goes through these issues with more detail, and it's very, very interesting. So this is what happened. You kick the garbage collector, and then you're good again, but obviously We've got obviously monitoring systems in the OS level where when your memory consumption goes over a threshold, then we shoot it on the head. And then, of course, then because of the security and to avoid other risks, so you don't want this to happen all of a sudden without any reasons. And yeah, as I said, monitor your system as much as you can. HTTP web servers, methods, codes, latencies. Yeah, we monitor a lot of things. We use Exometer. Well, today Exometer Core because it's been split up. And then we collect things with another library we wrote, and then we send them over to Graphite and so on. So as a final note, some of the open source contributions we've done, well, some of them are here. As I said, some of them have been merged upstream. A lot of our forks have a lot of interesting features that you're welcome to check out. And I'll hope you have enjoyed this talk. Questions?
Do you have customers?
Huh?
Do you have customers?
Sorry?
Do you have customers?
Yeah, we do have customers. We've been running, huh?
Repeat the question, please.
Yeah, sorry, the question is if we do have customers. We do have customers. We've been running production for a number of weeks, and we are onboarding customers as of now. And I'm afraid I can't disclose the number of customers or their names. So I don't think it's part of the scope of this. But yeah, you might find more information on layer.com about services or customers or any other info. Yeah.
Yeah, I have a question. Like, how do you make sure that your messages are not lost in case of errors?
You mean, for example, when you do a non-persistent delivery?
Yeah. So you have all these messages that are stored in your exchange or your queue, RabbitMQ, and suddenly that that server goes down, and there are like thousands of messages that haven't been delivered.
Yeah. So the question is, how do you ensure when you have problems with your queues? As I mentioned, when a channel gets killed by chance, then you lose obviously all those queues and so on. That's a very good question. That is only a it's not a problem to lose all that data because first of all we store all the data in Cassandra, and the routing messaging system that I explained is the infrastructure that we use to deliver messages when both ends are connected. That means when there is an established SPD connection. So when we're both speaking and there is a live stream set up, then we're going to have live messages that are going to be sent through a RabbitMQ infrastructure. If for some reason something goes wrong, right, the client SDKs implement a syncing protocol that are going to talk to our web framework API, and they're going to retrieve the latest message based on the RESTful interface. And that's like the other alternative that the clients have to fetch messages. But of course, I didn't go through that one because I didn't have much time. But yeah, obviously, if you lose messages, no problem because you can fetch them in some other way. Yeah.
Last question. What kind of scale did you test? What is the maximum number of clients that can be connected to the system?
Well, as we're speaking, we're doing a lot of load testing too, because we're looking at seeing how much we can grow. In terms of queues, we've been working on the numbers of 500,000 million queues per node. And then in product, well, when it comes to real connections, we're still working on our load. We've built a in-house load testing tool. So we're still working on scaling that up because fortunately or unfortunately, that tool is written in Java. So we're also having to scale that up in order to establish the right amount of connections with our server. But yeah, when it comes to scaling out the Rabbit to make it possible to do all the connections and deploy all the queues, we're talking about 500,000. That's what I got so far. And of course, that you can take it out and scale it out by adding more nodes. No problem, because we've clustered RabbitMQ.
That's all the time we have for questions right now. Sorry about that.
Okay.
Thanks again, Juan and Mark.